Hi everyone. This week we're happy to have Aron Wall here to tell us about some cool holography. Whenever you're ready.
Okay, so I'm going to talk about my work with my PhD students Gonzalo and Rifat on trying to modify ADS-CFT so that the dual field theory lives on a Cauchy slice instead of out at asymptotic ADS infinity. I should probably note that Gonzalo and Rifat are on the postdoc market at the moment, and they're both very good students. So if anybody is hiring, I hope you at least consider them. All right, so in the usual ADS-CFT duality, the dual CFT lives at spatial infinity. But recently, there's been a lot of interest in something that's called the TT bar deformation, or in higher dimensions, you'd call it the T squared deformation, which modifies ADS-CFT so that you are instead studying a holographic boundary that is at finite distance in the bulk. I'm going to postpone writing down the exact deformation, but the reason why it's called T squared is because it's quadratic in the stress energy tensor. So the idea is this thing is dual to a bulk where you impose something that's like Dirichlet boundary conditions for the metric and other fields. Okay, so the usual way people do this, I don't know how familiar people are in this audience with ADS-CFT. Who's seen the tin can picture? Okay, I'll explain it. So the asymptotically ADS space-time has the unusual property that if you conformally compactify its boundary, it has a time-like boundary. And so the geometry of ADS is, for purposes of causality, it's sort of like a half sphere times time. So the boundary is a time-like boundary. So when people study the holographic principle in ADS-CFT, the idea is if you have a quantum gravity theory in asymptotically ADS, where the known examples are usually various types of string theories, ADS possibly times some Kaluza-Klein compact directions, that this is a gravitational theory that is dual to a conformal field theory that lives on this boundary cylinder. Then you can start learning things, trying to use this dictionary between the two sides to say potentially more controversial things about like black hole evaporation or whatever. Okay, so in this case, empty ADS corresponds to the ground state of the CFT, and the conformal invariance is the same as the asymptotically ADS symmetry group. Now, because ADS has a time-like boundary, if you want to be really pedantic, it doesn't have Cauchy slices by the standard definition of global hyperbolicity, but it's possible it's fairly easy to modify the definition of global hyperbolicity to allow this. Roughly speaking, we want to say that a Cauchy slice is a surface. I'm going to draw this twice. So Cauchy slice is some surface in this interior that has the property that every complete causal curve intersects it exactly once. Now, the problem with an asymptotically ADS spacetime is that because there's a time-like boundary, the curve could go out to infinity and achieve an infinite affine parameter that way. The secret to defining Cauchy slices in ADS is simply not to consider such things to be complete curves, because they could indeed be continued if you just bounce off. All right, so this matches with our expectations of physics, because the usual reason we want to impose global hyperbolicity is so that there's some sort of determinism of the dynamics. And what people usually do in ADS-CFT is they impose some sort of boundary condition on the bulk fields of the interior, so that you do indeed have a well-defined evolution.
So sorry, just a quick question. So here you'll be considering only reflective boundary conditions at that time, like infinity?
There are other games you can play, but the usual standard setup is that, yes. As we can see, actually, we're going to modify this setup. Before we modify it, that's what you have, yes. Okay, so now you can ask what happens if you start with a holographic CFT and you deform it in various ways. The simplest deformations people think of, which correspond to what's called single trace deformations, just corresponds to perturbing the fields in various ways. But there's a more interesting deformation that's this T squared. That's an irrelevant deformation of the boundary theory. And what this thing does is, if you deform the boundary theory in this way, the usual way people think about it is that, so it was noted that if you do this deformation, which was actually originally discovered for D equals 2 QFTs more generally, because it had nice field theoretic properties, it was like an irrelevant deformation that was still fully well defined because of Zemeljakov discovered there's a factorization property. It was observed by some people, including Mark Bensay and some collaborators, that if you did this to a holographic theory, the effect of it was basically to move the boundary in to a finite radius like this. So the setup you now have is you'd have something like Dirichlet boundary conditions for the transverse parts of the metric on this cylinder that's at finite radius. It looks like it just moved a small bit, but because I conformally compactified, this thing's all the way out of infinity and this thing's a finite distance. So in the proper geometric sense, I actually moved it infinitely, but it's still in some sense a small perturbation from a conformal point of view. Or potentially small, depending on the coefficient of this, which could be small or large. So now you have something like, if I pick my boundary conditions here, it's now like reflecting boundary conditions off of this this time-like boundary that's at finite distance. Okay, so our setup is a little bit different. So it's going to correspond to this cylinder. So what we did is, instead of wanting to have an emergent space dimension, we wanted to arrange things so we have an emergent time direction, so that you impose Dirichlet conditions on the metric at one moment of time here, and then the past and future of that slice emerges in a sort of holographic manner from there. So this is emergent time. it turns out that you can actually do this with the exact same deformation. You just have to start in a somewhat different place. So I'll explain that in a moment.
When you say emergent space, are you thinking of the radial direction as being?
Yeah, the radial direction. Although strictly speaking, the Kaluza-Klein dimensions are also emergent. But I don't have anything useful to say about that in this talk.
Aaron,
Yes.
how seriously should I take this idea of the standard story for the cylindrical picture you drew there, the one on the left, is that as I dial up the deformation parameter, I get radial, I get a shrinking of this
That's right.
cylinder, it changes the radius there.
Yeah.
What would you expect to happen as you dial up the deformation parameter in the picture you're going to be telling us?
Right, I'll tell you about that in a moment.
Okay.
You actually have to dial the deformation up to a certain amount to get this picture at all.
Okay.
Okay. So there's also a sort of a philosophical difference between how you might be led to naturally interpret these pictures. In this setup, it's very sort of, you can't help but think of this thing as like a physical object that you bounce things off of. But when we impose Dirichlet boundary conditions on a Cauchy slice, we don't usually think of that as like a physical object. We just think of it as a way of specifying initial data. And that's more how we want to think about things. Okay, so we're not saying there's an actual like physical object that exists at one moment of time, so much as that this holographic theory is going to match on somehow to some state of general relativity.
Does the left-hand side picture actually make sense? I mean, in the sense that you needed a boundary at infinity to have a full complement of black hole states in your theory, and a dual quantum field theory, and now it's getting cut off. Right? Some of your large black holes aren't. How are you supposed to make sense out of that? Either gravitationally or.
Well, it turns out there's something. I mean, for a big enough black hole, you might think that this thing is behind the horizon.
Yeah.
And actually something extremely strange happens in this theory, which is that the energy eigenvalues become imaginary at that point. Maybe I should postpone discussion of that though. So, all right. So now let me write down sort of the fundamental equation of what we're looking for now. What we want is a field theory whose partition function is a Wheeler-DeWitt state of quantum gravity. Okay, so the fundamental equation that we're going for here is we have a partition function of this t-squared theory. That I'm going to write it as a function of g and maybe some other stuff is equal to a quantum gravity Wheeler-DeWitt wave function of g and maybe some other stuff. Okay, so at the level of the equation, we're saying that these are the same functions.
What do you do with the extrinsic curvature?
No, I'll tell you why in a minute. So even though these are equal as an equation, the interpretation is different between the two sides.
So what do you mean by the right-hand side?
This is a Wheeler-DeWitt quantum gravity wave function.
Which means?
A wave function in the canonical formulation of quantum gravity.
Okay.
Okay, so on this side, we think of this as like a fixed background metric. So this is a fixed background sources in a d-dimensional Euclidean field theory. So we're thinking of it like you think of, is this thing blocking the view?
No, the bag is.
Okay, well, I mean, if something's not visible.
But I
something
can,
say that.
I can, it's fine.
Oh, the backpack, okay. So so on this side, this metric is like a d-dimensional Euclidean space-time metric. I shouldn't really say time, but the point is it's the complete set of dimensions. If you were thinking of something like Euclidean signature Wick rotated field theory, okay? So you have a partition function. So this is a Euclidean metric, and there might also be other sources you turn on, like some scalar source, so that would be phi, and I'm just leg this standard for everything. Okay.
Sorry, in this Euclidean metric that you have there, would there be a direction which is kind of periodic? So you would, so fields,
No, not necessarily.
so that kind of different from the
It's-
usual Euclidean.
Think of it like quantum field theory in curved space-time. So you can pick what G is, okay? In that sense, it's not fixed, but we don't vary it in the path.
What are you taking to be the topology of the?
It's again variable. So you could change that.
It doesn't have to be flat.
In the case of a black hole, for example, you take over wormhole topologies. You had a question?
So you're imagining this to be something more like a Hartle-Hawking prescription for psi?
It feels a little like that, yeah. Okay, so if I were being pedantic because of topology, maybe I should write down the manifold too in this functional dependence, but I've been sloppy. Okay, on this side, we have the same set of objects, but we interpret them differently. On this side, I want to think of it as dynamical configuration space variables in a d+1 dimensional quantum gravity. Okay? So in the canonical formulation of quantum gravity, I can have like a wave function that's a function of the spatial metric, sometimes called Q, but I'm calling it G.
In the usual story without the t-square deformation, is something like this true? Because usually I've seen like people saying partition function is the same as partition function.
That's right, so they wouldn't usually write wave function, and that's what the difference because of this Cauchy slice.
I see.
There's some moral sense in which something similar you could try to think of the boundary CFT partition function as a wave function. There'll be a wave function in a very weird type of evolution that's purely radial, that is not the way we usually think about states in physics.
I seem to recall a paper by the Verlindes, maybe with digraph, ages ago, where they tried to recast radial evolution in the bulk of ADS in a formalism where you could think of it as like a Wheeler-DeWitt.
That's right. So I think that's definitely in the literature and is used in this subject. So at some level, what we're doing is we're taking this known thing and we're reworking it to be back to the original way people thought about Wheeler-DeWitt.
Got it.
Okay. So now I didn't realize this till I started teaching holography. But what's really going on here is the thing that makes holography function is that there's sort of dual notions of a conjugate variable. So when you have partition functions, you have, like if you're doing thermo or QFT, you have a natural notion of a sort of a symplectic structure between sources and operators, stating this in the QFT language. So it would be operators. So these are the things, sort of the sets of variables that your partition function depends on, or the dual set of things that tell you the gradient with respect to thermodynamically or field theoretically conjugate things. But in mechanics, And psi sort of stands for this mechanics side, quantum mechanically, but classically in mechanics, you have a symplectic structure between position and momentum variables. Okay, so what holography is really doing at some level is, even though when these are originally introduced, these are not the same concept, the duality actually relates these two to each other. So that what you're saying, things that you would interpret as being sources from the field theory side, you reinterpret as being dynamically evolving fields from the mechanics side. And so this actually now answers John's question, why is this thing a functional just as the metric and not of the extrinsic curvature? Well, it's sort of like the standard quantum mechanics reason why you make a wave function of position but not momentum, but the momentum is still there with the Fourier transform. Okay, and it is related to the differentials. Now, if we have a partition function, what's the basic game we play with it is differentiating with respect to the sources to get the operators. So an example of this, the most obvious thing to do is to take a variation with respect to this metric. And this has a different interpretation on the two sides. So if we're on the partition function side, then up to some not very important and somewhat conventional factors, we would say that this is how we define the stress energy tensor of our field theory. On the other hand, on this side, up to a factor of I that is actually important and possibly disturbing, this is how we would define the ADM momentum. That is the thing that is related to the quantum mechanics conjugate to the metric that in GR is like related to the extrinsic curvature. I think like that. So it's important to keep this straight. The stress tensor of the field theory isn't dual to the stress tensor, it's dual to the extrinsic curvature. Okay, so it gives you the other degrees of freedom you need classically if you were doing a full phase space. Now, this factor of I said you might be disturbed by this, as well you might be, because it implies that in the Cauchy slice, I'm defining pi, AB, in such a way that it is real in Lorentzian signature. So that means that the stress energy tensor is imaginary. So this is not a conventional unitary field theory. And this is actually, so at some level, this is something, if you're going to do this at all, you just have to bite the bullet, because the Wheeler-DeWitt wave functions definitely do not satisfy the reflection positivity property that would be required by any unitary field theory. So this should, by the way, not be confused in any way with the type of unitarity people discuss in the context of black hole evaporation, which is about whether pure states evolve to mixed states. Here, we're talking about something that's ends up being more closely connected with whether the norm of the theory is always positive. So this is actually associated with the phenomenon I'm about to show you, which is that this theory exhibits an exotic phenomenon that I call CPT, spontaneous CPT breaking. So the CPT time reversal is going to be broken in certain situations in a way that actually breaks CPT. And this is actually a necessary property to recover Lorentzian signature. But in fact, the broken regime is effectively tells you that your bulk is Lorentzian instead of Euclidean. But this cannot happen in a traditional unitary field theory, basically because of the CPT theorem, which involves unitarity as one of its assumptions.
Do you mean by time in this kind? Because we're on this slice.
I'll show you. It's the time of how it's embedded. So was there
I was just going to ask what assumptions in CPT break, but you
Right, so the famous assumption of the CPT theorem is Lorentz invariance. Since we're in Euclidean signature, that's just rotational invariance of the theory with this Euclidean metric. That's not broken, but there's a second assumption, which is unitarity. One way to state the CPT theorem that makes it sound a little obvious, and there's a few subtleties with this, but it's roughly, in Euclidean signature, it's roughly speaking the statement that reflection positive theories are necessarily reflection real. If you look at the endpoint functions. Because positivity is a stronger condition than reality. Okay, so what I want to do to show this effect is I want to start with a Euclidean, Witt-rotated, holographic CFT. Defined using a metric GAB. Now, because this is a conformal field theory, if we were in odd dimensions and there's no conformal anomaly, you might think only the conformal part of this metric is going to matter, but we're about to turn on an irrelevant deformation, so in fact the conformal part does matter, because the theory won't be conformal after we've broken it. So now, and then we're going to turn on this irrelevant deformation parameterized by a parameter mu. So deformation is 0, but mu is 0. Okay. Now, if we pick the simplest case to consider is just as an example where there's more symmetry, it's in no way the only example you can consider. But if JB is a uniform hyperbolic geometry. So that's like, so in the picture, if you have a Euclidean holographic CFT, hyperbolic space has as its boundary a sphere, okay? And now, if you take just the bottom half of that sphere, that is conformal to hyperbolic space, okay? So we can start with this bottom half here. To get a complete partition function, you need to put in boundary conditions here, but it doesn't matter for purposes of what I'm about to say because of all the symmetry. So what happens is you started with the Euclidean CFT here. This is the moment of time reversal symmetry. As you turn on this deformation, this thing moves a finite distance into this, at the moment, purely Euclidean signature bulk. As you increase the deformation, it moves towards this imaginary time equals 0 slice. And at a certain critical value, it moves into the Lorentzian signature ADS space-time. that looks like this. They're joined together at the t=0 slice. So this is like where the Euclidean contour meets the Lorentzian contour, and above the critical value, it bulges entirely. Yes?
So I'm afraid you've lost me here. You were talking about doing a deformation of your field theory, which I would think of as a deformation of the way that the partition function depends on the metric and the sources. That's what it would mean to me to change a field theory. But what you're telling me now is that the way I should think of that is that as I dial my deformation, the metric on which my field theory is defined changes. And I don't understand the connection between those two things.
Okay, so it's just a rescaling. So there's actually a relationship because you can set things up so mu is the only dimensional parameter in the problem. And if you do that, varying mu is equivalent to rescaling your metric.
That seems really far from obvious to me. Is there a...
Well,
If
we
I have to
started
just
the
take it on
CFT
faith.
and we deformed it by a dimensional coupling. So unless we do something, so you're okay with the idea that this is the only dimensional coupling?
Sure.
Okay. Then anytime you have a theory with one-dimensional coupling, rescaling the metric is necessarily equivalent to rescaling the size of that coupling, just because the metric is, by definition, the thing in your theory that tells you what size things are.
That would make me happy with the idea that between mu equals 1 and mu equals 2, I could realize that difference by rescaling the metric. But what about mu equals 0?
In that case, the scaling goes to a bit. Perhaps you would be happier with this. We could pick mu to be constant, and then I could just rescale the metric. And so I'm just changing like the radius of the hyperbolic space. And then that radius would tell you where you're embedded in this diagram. And the CFT limit would be some degenerate limit of that. Are you okay with that picture?
I think I'm okay accepting it as a claim that I, without seeing the details, that I can accept and understand the rest of what you have to say.
I mean, it looks like there's 2 degrees of freedom, which is the hyperbolic radius and the size of this coupling constant, but because of rescaling, there's really only one parameter to play with. Okay. So there's ways of doing it that make the CFT limit look nice, and there's ways of doing it that make getting the Hamiltonian constraint look nice. But
Are you saying that there's some critical value of mu?
there's given a fixed value of the hyperbolic radius, there's a critical value of mu, or if we fix mu, there's a critical value of the hyperbolic radius.
And
It is
what special
the
thing is
critical
happening?
value has to do with the radius of curvature. So if you take this t=0 slice, it has an amount of negative curvature that's basically just the negative curvature radius. So it's about whether you have more positive or more negative curvature than that. And this is all controlled by the fact that, for reasons I might eventually get to, this partition function is constructed so it obeys the Hamiltonian constraint equation, as it's going to have to if this equation is right. So because of symmetry, we only need to concern ourselves with the trace of the extrinsic curvature. And the Hamiltonian constraint equation is roughly something like the pi squared is given by minus r minus 2 lambda, where lambda is the bulk cosmological constant. So the statement is that if you're considering the slice where it's more positively curved than the ADS curvature, then you end up with Euclidean signature. But if it's more negatively curved, you end up in Lorentzian signature. when you do end up in Lorentzian signature, so
Is the sign there the one that takes account of this I?
yeah. If I got this right. That was the intention. I mean, I'll flip the sign of pi squared. So probably it's right, or why would I have bothered to put the minus sign? So what's definitely true is more negative curvature should get you in Lorentzian signature, which should correspond to pi being imaginary. So here the Cauchy slice bulges up here in how it's embedded. That is, since we calculate the extrinsic curvature, we sort of think of it as embedded in a high dimensional space. But of course, there's an equally good slice with the exact same geometry that's embedded to the past. Okay, so the theory doesn't tell you which of these pick. That's why I say it does both. It's spontaneous. The partition function should be a sum of two terms, one of which is this and one of which is this, and that would spontaneously break time reversal invariance. In Euclidean signature, time reversal invariance is complex conjugation. And so if the stress tensor is plus imaginary or minus imaginary, that would be the choice that breaks this. So it breaks T. And in this particular setup, there's C and P are untouched. That's why I say it breaks CPT as well. It would be much more conventional if it broke T while also breaking CP. Then there'd be a bunch of condensed matter. This is something stranger. Okay. I should say, I think maybe I mentioned this. More generally, if you want to figure out what the stress tensor is, you have to worry about boundary conditions or make a closed partition function. It's really the extra symmetry of this case that makes it that everything is controlled by the Hamiltonian constraint. And as long as you assume the symmetry is respected, you get a definite answer. Okay, so now I should write down what is the deformation that actually does this. So we were inspired by the work of Hartman, Kruthoff, Shangelin, and Tajini in 2018. So I'm going to write a bit of a beast here. So, but don't worry, I'll explain it. Okay, so this is the CFT partition function. Let's assume, just for the sake of simplicity in this talk, although we consider the more general case in our paper, let's say we're working in odd dimensions and more generally in the case where we don't have to worry about trace anomalies. Okay, so that means that because this partition function is conformally invariant, if I insert the trace of the stress energy tensor here, then that annihilates this expression. If I insert it here. The goal of this stuff is to construct a deformation that has the property when I commute this thing past all of this stuff, it should look like the Adiab Hamiltonian constraint. So the point is, this counter term here and this deformation of lambda are chosen to be what they need to be for that to be true. This is a path-ordered exponential from over all the values of this deformation parameter. Lambda is just a dummy variable for mu. The reason there's this path-ordered exponential, this is how it's not how it's usually explained, but the basic physics of this idea is if you turn on infinitesimally this operator, it should be something like the stress tensor squared. But as soon as you do that, the stress tensor changes because you changed your theory. And the idea is that as you flow along this deformation, you're supposed to, at any given point in this flow, you're supposed to be using whatever the value of the stress tensor is at that point in the flow. In our notation, that is implemented by this path-ordered exponential, by taking O to include differential operators with respect to the metric. O here, this thing, in order to preserve locality and covariance, this thing just wants to be a local covariant integral. And we have a procedure. If you start with the Hamiltonian constraint of the associated dual theory, we have a procedure for using that to figure out what x of these counter terms are. In light of time, I think I will not go into too much detail about that. I'll just give an example. So if the bulk theory is 3 + 1 general relativity, pure gravity, then the counter term is just of the form volume plus an Einstein-Hilbert term. And the X deformation is something that is quadratic in the stress tensor. This looks like the kinetic part of the idiom term. And then there's some extra terms involving the Einstein tensor. And times the stress tensor, and then just the Einstein tensor squared. So these are all constructed in a way that makes the kinetic term look right. The Einstein tensor basically rises because after you shift by this counter term, that's what ends up giving you the spatial curvature part of the Hamiltonian constraint. The various powers of lambda that appear in this expression ensure that the property I said holds, that mu is the only dimensional thing of the problem. That's also why we divided by lambda, to keep this dimensionally neutral. That's just a convention. But arranging things in this fashion leads to dramatic simplifications in the algebra. If you try to write down a general deformation without this principle, that mu is the only dimensional parameter, you end up in some very bad places. In this case, when you commute pi past all this stuff, it closes after a single extra term. If you don't arrange things very carefully, you have infinitely many terms. So that's why you do things this way. Yes?
Can you tell me again, once you commute pi through, it becomes the Hamiltonian constraint. What is it when it's just acting on the CFT partition function?
Well, here it's just the trace of the stress tensor. That's when.
It's the trace of the stress tensor, or it's the functional derivative that will?
It's the functional derivative with respect to the
give you the
metric contracted with the
function.
metric itself, which is what we call the trace of the stress energy tensor.
So I'm sorry, but I thought you wanted this thing to be 0 because you wanted it to be.
It's 0 if you insert it here.
Sorry, but G is curved, right? So what about the trace anomaly?
I just said for simplicity, we start in a case where there is no trace.
I'm sorry, okay.
You can have a trace anomaly, but then there's some log divergences in here, and you have to cancel it out with something that's marginal, that is log divergent at the lower end of this.
Okay.
This thing was originally done at d equals 2, where of course the trace anomaly plays a very important role, and actually is what gives you the R term in that case. This is how things work at d equals 3. Okay, so I don't want to spend too much time on that because the important part is just to arrange this property so that the Hamiltonian constraint annihilates the partition function. I should say this counter term piece is not super conceptually important because it just acts by some sort of similarity transformation on the field. So this is sort of just like a field redefinition to make it so that the Hamiltonian has the expected form instead of an unexpected form that is still physically equivalent. Okay. So instead, what I want to do is I want to talk about how you use this to explicitly construct a geometric dynamics dictionary in ADS-CFT. So suppose I give you bulk data that says I give you a wave function and you want to know what is the corresponding CFT state, or vice versa. I have a CFT state, I want to figure out what the corresponding bulk state is. So our claim in our paper is that if you know this t-squared deformed partition function explicitly, then you could use it to write down simple maps relating the bulk of the boundary. So the first map is the bulk to boundary map. So here, I imagine specifying some data on the Cauchy slice, just configuration space data, doesn't need to satisfy any constraint equation. So I can just pick some metric and sources. Now, whatever I pick here, this defines a partition function with an open boundary. In general, a closed partition function gives you just a number, but an open partition function gives you a state on the boundary because its value depends on boundary conditions. So we now say that you can define a CFT state. So all of this, in case we have an open partition function, it should also depend on some data associated with the boundary. And we just use the notation that we call that data chi. So that's actually on both sides here. This could be any basis you like for the CFT. So for example, an energy eigenbasis. Doesn't matter. Discrete or continuous. So if you want to write the CFT wave function in this basis, then that's just going to be this partition function as a function of the stuff that you pick. And also this boundary data, which you leave open. And so this equation makes sense. So it's a very natural way, given sources in the interior, you get a boundary state. On the other hand, there's also a boundary to bulk map. And that works a little bit differently because of the Hamiltonian constraint. So if I specify some state on the boundary CFT here, it's unreasonable to think that this state will tell me what Cauchy slice I have in the interior, because GR is a theory where time translation is a gauge symmetry, except on the boundary. And so a Cauchy slice here is equally good as a Cauchy slice here. You know, there's all sorts of Cauchy slices in this Wheeler-DeWitt patch. So I can't get something that just tells me one of these. I can get a wave function that's like a superposition of all of these. And that's what happens. So here we have a Wheeler-DeWitt state that satisfies the constraint equations. I should mention I made a big deal about how you construct this to satisfy the Hamiltonian constraint equation. The spatial momentum constraint equation follows pretty trivially because that's just a statement of covariance in this field theory. So as long as you pick this to be a covariant integral, you always get that. It's just conservation of the stress tensor from the field theory perspective. So here we write, and this notation presumes chi is continuous, but you can just replace this with a sum if it's discrete. So this is just the partition function, but you trace out, you multiply it by your CFT state. So basically what you're doing is now you're tracing out the chi degrees of freedom, and now you're just left with a amplitude for any given metric and other fields of the interior, which is a wave function. Yeah.
What bulk state do you expect to get from this dictionary you originally wrote without all the chi's? If you don't specify a wave functional boundary?
The chi's have to be here because these things aren't well-defined objects until you put in boundary conditions. The argument that the Hamiltonian constraint is satisfied is independent of the boundary conditions. But it means that in a situation like asymptotically ADS, where you have a boundary which is open, you have multiple states.
Oh, right.
Whereas in this formalism, which you expect because the CFT has multiple states.
G is not compact.
No,
G that
unless you can formally compactify it. But it has a boundary.
I see. Okay.
So yeah. Now, if you try to do the same thing for a closed universe, you would instead get a unique state. So, which is of course many fewer states than at least semi-classically you expect to exist. So that is a more philosophically challenging application of these ideas that's much more confusing. But here in this asymptotically ADS context, you get multiple states. So yeah, in this dictionary, we showed that you can how to explicitly map between the bulk quantum gravity Hilbert space and the boundary quantum gravity Hilbert space. And so one thing you might notice is these maps aren't exactly inverses of each other. Because this map always gives you a state that obeys the Hamiltonian constraint equation, whereas here you start with arbitrary data. Our belief, our hypothesis, basically our statement of what it means for this holographic idea to be correct, we state it more generally in the paper, but if our idea is right, then what this should be, at least in semi-classical situations where you could check it, is if I compose these two maps to get a so if I compose these two maps to get a bulk map, that's something where I put in data on one Cauchy slice, and then I give the amplitude for data on a different Cauchy slice, and we believe this should give us basically the gravitational path integral. So if I do the gravitational path integral, I would define a dynamical quantum gravity inner product to be a path integral between one metric and another metric of integrating over the d plus one dimensional metric over the diffs of e to the minus action of g. So this is a Lorentzian path integral. So it should be plus or minus I, where the sign depends on whether you let the lapse be positive or negative, and we argue we should include both sides, which is one of those controversial quantum gravity questions. We had to have a fair amount of discussion in our paper about just the semi-classical, or not just even semi-classical, about the quantum gravitational path integral, just to figure out how it works on its own terms. Of course, even if you originally approached holography from the perspective that it's a way to circumvent defining geometric dynamics quantum gravity, and if you want to show that it gives rise to geometric dynamics in some regime, you still need to understand all this stuff. So we were forced to confront all of this, making sense of Wheeler-DeWitt and the gravitational inner product and such. Okay, so this is a brief sketch of what we've done. In future work, because this is an irrelevant deformation in greater than 2 dimensions, it's not actually completely obvious it makes sense as a field theory, and we're exploring the idea of whether it can be UV completed in some way, which is plausibly easier than trying to UV complete traditional quantum gravity. And if we did so, we think it would give a definition of bulk quantum gravity by these maps. So that seems interesting. I've also been working on calculating microcanonical entropies of this theory. You get the interesting property that you recover entropy equals A over 4 for marginally trapped surfaces, but you get bigger, smaller answers for other kinds of surfaces. So I was discussing that with some people at lunch, but I think this is enough for one talk, so I'm going to end here.
Thank you, Aron. Do we have any further questions?
It's a very, very interesting, very provocative talk. I'm just trying to wrap my head around the structure a little bit more.
Yeah.
So your CFT partition function acted on your path order exponential. Does it obey any nice differential equation in lambda? Or mu rather?
Yes, it does. I mean, it can also
Just
be
what we'll
defined,
do
it can also be defined by a differential equation.
The other thing I'm confused about is the x dependence of your operator.
X like the spatial coordinate.
Yeah. I mean, I guess there's a question again of defining this above 2 dimensions.
I sort of erased it here, but it's an integral over something that looks like a local differential operator at any point of this deformation. So it's the fact that it's an integral is what makes it convey. Normally when we perturb a Lagrangian, we perturb it everywhere, so that's the integral. But because we integrate this deformation by a finite amount, it could be doing something, and for a finite value of this parameter, it could be doing something very non-trivial to how things are localized in the theory.
I don't know. If we drop down to d equals 2, where there was a lot of magic, does all of this story simplify in some nice way?
Yes, but I believe the simplifications are fundamentally connected to the fact that d equals 3 quantum gravity has no local degrees of freedom. So the statement that's true for every d equals 2 QFT is that if you write down this particular combination, the particular quadratic combination of the stress tensor you like, which is called TT bar, because it's like left moving times right moving, but then there's also some trace squared piece. So that there's a magical factorization property that follows only from translation invariance and conservation that makes it so when you write down this operator, so this is a function of the stress tensor evaluate same point, but it turns out it's translation invariant where you can translate one of the stress tensors relative to the other and you still get the same answer. Okay, so this is a magical thing that happens at d equals 2 that makes it so the theory is actually at the level of the spectrum. It's exactly solvable. Okay. Now, you could do this for any quantum field theory, and in a holographic theory that's dual to pure gravity, it's the right thing to move things in. But if you now added a scalar field, and you want nearly boundary conditions for the scalar field as well, it turns out you have to add something else to this deformation that's like basically related to the operator associated with the scalar field squared, and that spoils this factorization property. So anytime you have a theory, a non-trivial quantum gravity theory, in a sense that has local degrees of freedom, I believe you're going to end up with a field thing that requires UV completion, maybe a conservation of difficulty thing.
So your initial TT model works for any quantum field theory, right? Holographic or not. It wouldn't have to be pure gravity, right? I mean, in
A
principle.
lot, right? So, but if you want to be working in a regime where we have confidence that we can do computations, then you want to either be doing this d equals 2 deformation, or you want to be doing the large n thing, which allows you to factor. So I stealthily put this normal ordering around here. So we believe that you can take into account like 1/n corrections, which are like quantum loop corrections of the bulk, by treating this as a quantum operator. But its interpretation at finite n, it's not completely clear that this thing makes sense. So one way to see it, for example, is if I started with a completely random 3-dimensional CFT that is not holographic, then there's no guarantee that there even is an operator whose dimension is twice that of the stress tensor. Because while the dimension of the stress tensor itself is protected by conservation, the dimension of the stress tensor squared could pick up some anomalous dimension. Okay, so holography actually guarantees that there is an operator like this, or if you start taking into account when a random correction is an operator sort of like this, that you could work with. And that's, of course, associated with the fact that this bulk theory is a theory where gravity is weakly coupled, where the gravitons are going to end up being approximately Gaussian, and where you can therefore talk about products of fields in a sensible way. Now, I believe in an ideal scenario, we figure out ways of UV completing this, and then we can also talk about much less geometrically classical theories at the full-blown quantum gravity level, but this is just where we are right now.
If there aren't any further questions, let's thank Aron again.